Okay, so today what we are going to do is what all problems or what are the applications of Morse circle in geotechnical engineering. Okay, now we can see the soil wedge that I have drawn here. Okay, I've seen it before also, GOH. This was probably discussed in the first lecture on shear strength. Now what is this GOH? It's a soil element which you are considering 2D. You're not considering it in 3D. Okay. And this soil element is failing along GH. So the arrows which are perpendicular to GH are indicating the normal stress. Okay, and it's sliding along GH. It is getting cut along GH. So the stress that is indicated along GH is called shear stress. Okay, shearing is another word for cutting. Right. Now, what is sigma 1 and sigma 3? Sigma 1 is the major principal plane and sigma 3 is the minor principal. Now, the first objective that we're going to discuss is this particular case when sigma 1 is non-horizontal and we want to indicate GH on the Morse circle, and we need to determine the direction of sigma 1 knowing the direction of sigma 3 and values of sigma 1 and sigma 3. What are we trying to do? We are trying to find out the direction of sigma 1. We are trying to locate GH on the Morse circle. What is the data that we have? We have the values of sigma 1 and sigma 3 and we have the direction of sigma 3. So how do we start? We have x and y axis. On this x-axis, first thing is we mark the point A. Okay. How do we mark point A? This is equal to what? What will be this? Sigma 3. Then we mark the point B. How do we mark point B? Distance between origin and B is how much? Sigma 1. Once you know A and B, you get the midpoint of A and B. You have the center of the Morse circle. So I have drawn a Morse circle, taking this point, midpoint, and name this as C, and taking AB as the radius, I have drawn this circle. Now what is the next thing I do is, I will draw a line which is parallel to the direction of sigma 3. So you can see here O and H. Yes. So I'm going to draw a line through point A, okay, parallel to the direction of sigma 3. And wherever it cuts Morse circle, I will name that point as P. Okay. So while I am doing this, you will also do this. Okay, and make your own notes because I am not going to give any notes. Okay. So what is this line? This line is parallel to direction of sigma. Then what I do? From P, okay, I draw another line which is going to cut B. Okay, so what I am doing? I am taking P and I am drawing a line which is going to cut P. So B, sorry. So take another line which is going to, sorry, I have used the wrong weight. So take this. So from P, I am going to draw a line which is going to cut. Okay. Now, what have I achieved by doing this? If you realize, what is the angle between sigma 1 and sigma 3? This angle, it's 90 degrees. What will be this angle APB? It has to be 90 degrees because I have drawn a this particular APB is subtending the diameter. Okay. Now further on what I am drawing, you all don't draw. If I draw any line, okay, which is subtending the diameter, any angle like this, what will be this? This will be all 90 degrees. Why? Because they are subtending the diameter. Circle geometry, right? We studied this in school. So now I drew this first line at sigma 3 parallel to sigma 3 and second line to intersect at E. Automatically this second line is actually going to indicate, what is it going to indicate? The direction of sigma 1. Okay, so this is the line which will indicate sigma 1 direction. Are you understanding why? Why it will indicate sigma 1 direction? Because this is the direction perpendicular to sigma 3. Which is the direction perpendicular to sigma 3? Sigma 1. Right? That's why this particular line is representing the direction of sigma 3. Now, next is I need to, okay, before that, just write down a small line. Okay. Point P. Okay. Point P is called origin of plates. Okay. Or it is also called O. Okay. Now, so far from this Morse circle, what all things I know? Can I find out? I know the magnitude of sigma 1, I know the magnitude of sigma 3, I know the direction of sigma 3, and I know the direction of sigma 1. Now, the next thing I need to find out is the direction of GH. So, what I do, from point P, I draw a line parallel to GH. From this point P, I draw a line which is parallel to GH. So what I have done now? I have taken a line from P parallel to GH. So this particular line is parallel to GH. Wherever it is intersecting Morse circle, I will call that particular point as N. Now what is the importance of this N? See, I have got the direction of GH. What I need to know is what is the amount of shear stress which is experienced by this plane and what is the amount of normal stress which is experienced by this particular plane. So on the x-axis we have normal stresses, on y-axis we have shear stresses. Now, if I find out the x and y coordinate of M, will I get the shear strength and the sigma, that is normal stress, shear stress and normal stress experienced by this particular soil element along GH, right? So, now, when you draw, you can put this in step further. When you draw a line parallel to P, okay, parallel to GH from P, you get point M on the circle and X and Y coordinates of this M will give tau, that is shear stress, sigma, okay, experienced by element along GH. This is the first application of Morse circle. Now look at these two grey lines that are drawn. When I join M with the center of the circle, the angle subtended here, okay, here is 2 times alpha. Okay, what is alpha? Alpha is the angle made by the failure plane with the major principal stress. Okay, so from the Morse circle, if you didn't know the value was not given also over here. Just connecting M with C and B, you would get the value of 2 alpha. And now you know this is the radius, this is also radius, this is isosceles triangle. So by geometry, you know this is alpha. Okay. Let's say, what if my major principal plane was horizontal and minor principal plane was vertical? Okay. That is my major principal stress, sigma 1 was acting in a vertical direction and sigma 3 was acting in a horizontal direction. then how will my Mohr circle look? So how will you modify Mohr circle for this case when your sigma 1 is horizontal, sigma 1 plane is horizontal, the stress is acting in vertical direction, and minor principal plane sigma 3, the plane is vertical and the stress is horizontal. Are you understanding? I hope I'm not confusing here. Okay, what I'm trying to say is, you can see the major principal plane is this GO. This is going to be horizontal. The stress is going to be acting in vertical. If this is horizontal, the stress is going to be vertical. And OH is the plane, minor principal plane. Sigma 3 will be acting in horizontal direction. The plane will be vertical. So in that case, how will I modify my Mohr circle? Okay. So first thing, you draw the Mohr circle, you know the value of sigma 1, you know the value of sigma 3 is sigma 3. You mark point A and B, and the center point of A and B will be the center of the Mohr circle. AC will be the radius, you draw the circle. Okay, the horizontal axis is going to represent normal stress, the vertical axis represents shear stress. Now, next thing is, you know that the minor principal plane is vertical. So, through A, I'm going to draw a vertical line, and this is right. Okay, so it's going to be asymmetrical. Now, one thing you have to understand is, because major principal plane is horizontal, now point P is going to come on the point A. Okay, what is point P? Point P is pole that we studied. Here we studied point P is the pole. Now where will that point P lie? It will lie on the point A. So on this itself, so P lies on the x-axis and coincides with the point A. So for any point on this circle, y-coordinate would be maximum when M coincides with a point which is at the apex, at the highest point of the circle. Right? Where will be the maximum y-coordinate on this circle? Somewhere where the point is right on top. So I'll name this point as, let's say, C dash, and the point right below it, I'll name this point as C double dash. So now M, that is a point which is representing your, what is M representing? M is the point representing your failure plane. This M is representing GH. I told you every point represents a plane on the Mohr circle. So, when will be the maximum y-coordinate of M? When M will coincide with C dash. So, I'll mark this point itself as M. Okay. So, you can write down over here. Since C dash represents point of maximum shear stress, N will coincide with C dash for max tau. Okay. Now, PC dash will represent the plane on which maximum shear will occur. Why do I say that? Because this C dash or M has the point by coordinate maximum value of tau. Correct? What will be PC dash, C double dash? C double dash is the point where maximum negative shear is going to occur. And from the geometry, you know what will be this angle CPC? It will be 45 degrees, right? Now we all know that the maximum shear stress will occur on the plane PC dash or PN. And why? Because this point has got the maximum y coordinate, right? Can you tell me what will be the value of this y coordinate at this point C? What will be the value? So maximum shear stress will occur, and which will be equal to, will that y coordinate be equal to the radius of the circle? And what is the radius of the circle? Radius of the circle will be nothing but sigma 1 minus sigma 3. That gives you the diameter divided by 2. Okay. So now we can conclude that shearing stresses on planes inclined at 90 degrees are equal but opposite in sign. Okay, so these planes or these stresses are called conjugate shearing stresses. So what you see on PC dash and PC double dash are called conjugate shearing stresses. And the maximum shearing stress is called principal shearing stress, which is equal to sigma 1 minus sigma 3 divided by 2. Now, also maximum shear stress will be on which plane it will act. So this maximum principal shearing stress or maximum shearing stress will act at 45 degrees to PPL, principal plane, major principal plane. Major principal plane. Okay, there are some more conclusions which can also be drawn from this circle. Let's study which are those. Now there are certain conclusions that can be drawn from Morse circle. If you look at this particular figure which is on the screen, okay, this is just an extension of the same figure which we had drawn before. I have just connected N to O now directly, okay, origin. So if I have to find the magnitude of resultant stress, okay, how will I get it? It is given by under root of sigma squared plus tau squared. Okay, and this angle ONC or ONM dash is called beta, and that is called obliquity. Obliquity is given as tan inverse of tau by sigma. So if you know the obliquity, you can state, can you write this equation? Tau is equal to sigma times tan of beta, tan of obliquity. Now, maximum value of obliquity, okay, I can write it as beta m, okay, of the resultant stress will be at a point m. Okay, now when will I get maximum beta? Where should I place this m? Do I place it right on top? Will I get a maximum obliquity? Tau by m. Think. If I keep it right on top, will I get maximum value of obliquity? See, obliquity is basically you have to draw a point from O, okay, tangential to the circle. Okay, so if I have to select a point on top here, okay, if n goes up, will that value be maximum? Let's draw this and understand. If I select this point right on top here, okay, and I connect it, I draw this, let's draw and see whether, is this value going to give me maximum beta? See here, now I'm taking some other point M, which is below. Let's say I take N here now. Now I connect this. I'm getting still higher value of beta. Are you realizing this? Which is the point with the maximum value of tau? This gray point, right? And at this point, where red line is drawn, at this point tau is not maximum, but the obliquity is maximum. Can you see that? So, and erase all these things that I've done. So, if I have to find the maximum value of obliquity, it will be at a point which is lower than the point of maximum shear. So, I've drawn this new diagram. You are also draw this. Okay, so a point N O such that OM is tangential. Okay, I will mark all these points A, same as B. Okay, then C, and this will be C alpha F. With this 2 times alpha F, failure plane. Okay, this is for C is equal to 0. That is cohesionless soils. Okay, please remember that. Otherwise, this envelope will not pass through region. Okay, so now I'm not marking the sigma 1, sigma 3 and sigma 1 minus sigma 3 by 2. All these things I'm not marking. Okay, you all can mark all these things. So at a position where N is actually not a point of maximum shear, you will realize that obliquity is maximum. Okay. Now, criteria for slip failure, this is very important. Criteria for slip failure is not maximum tau but max obliquity. Okay, so criteria for slip failure is when beta will reach Bn, that is equal to 5. Okay, the failure will occur. What is obliquity? The maximum ratio of the shear stress to normal stress. Tau by sigma will govern more than maximum tau. So you will understand that the failure need not occur in a particular slope because the shear stress has reached its maximum value. It can also be because beta has reached its maximum value. That's why usually that's why there is a limit at which you can cut a hill. You can't cut it too steep. Why? Because it will fail because the slope has reached its maximum value. Okay? It is very much clear that the failure will occur along the plane Pn. So I have drawn here Pn. This will be the failure at which the plane at which failure will occur, and Pn is called critical plane, or it is also called failure plane. Okay, from the circle geometry you can derive this equation that the maximum obliquity, okay, the relationship with sigma 1 and sigma 3 can be written as sine of beta m is equal to sigma 1 minus sigma 3 upon sigma 1 plus sigma. This is from the fundamental circle geometry. You can derive this. Okay, I don't want to go into a derivation. And from this you get an equation sigma 1 upon sigma 3 is equal to 1 plus sine beta m upon 1 minus sine beta m. Mind you, this is for cohesionless soils. Okay. Now the angle at which critical plane or failure plane meets with the major principal plane, that is alpha f. Again, this can be derived. I don't want to go into derivation. You are going to refer the book. Okay, alpha f from the basic principles of circle geometry you can find out is beta by 2. What is alpha f? The angle that critical plane or failure plane makes with major principal. Okay. The general equation for C5 soil says sigma is equal to sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 alpha. Okay, so far we have only been discussing C is equal to 0, that is cohesionless soil, that alpha value that we got 45 plus maximum applicability by 2 is also applicable for C is equal to 0. When I substitute this alpha in this particular equation, okay, and I substitute this particular value and simplify this equation, I get sigma at failure can be written as sigma 3 into bracket 1 plus sine of beta n is equal to sigma 1 into bracket 1 minus sine of beta. Now what happens for clayey soils or C5 soils, we will discuss later. What we will do is we will, with these equations itself, we will first solve a problem. Then we will go to C5 soils. Okay. Okay, now we're taking an example, a numerical. This is taken from one of the textbooks, I think it's given. Okay. Direct shear box test performed on a removed sand sample yielded the following observations. Normal load is 0.36, shear load is 0.18. Sample area is 36 cm square. What you're asked to find out is the internal friction angle, that is phi. Then the magnitude and direction of principal stresses in the zone of failure. Magnitude of maximum deviator stress. Okay. If the sample with the same Morhrs ratio, that is same E, was tested with an all-round pressure of 60 kN per meter square in a traction test solution. So assume C is equal to 0. Now let's solve this. So now the first thing is you're given normal load and shear load. You need to convert it into normal stress and shear stress. So divided by area. Now using Coulomb's equation, we get tau is equal to sigma 10 phi. What is your Coulomb's equation? Tau is equal to C plus sigma 10 phi. Why I am taking directly writing sigma 10 phi? Because C is equal to 0. It's given in your problem. Okay, Coulomb's equation is not this. It's tau plus sigma C plus sigma 10 phi. You know this, right? So now from here, you know the value of tau, you know the value of sigma, you can get the value of phi. Okay, so you get tan of phi is equal to tau by sigma, that is 50 by 100, it is 0.5. So phi is equal to tan inverse of 0.5, that is 26.6 degrees. So your first part is determined. Now, we also know when tau is equal to sigma 10 of beta m. Where did we study this? Maximum obliquity. Right? We have already studied maximum obliquity is always equal to phi. Therefore, beta m, that is maximum obliquity, is also equal to 26.6 degrees. Now, the next thing you are asked to find out is magnitude and direction of principal stress in the zone of failure. Now we have this equation sigma is equal to sigma 1 into 1 minus sine of beta m. Very simple to memorize, right? Where did we study this? We just studied it here. Right? For C5, just now we studied this. So we use this equation to determine the sigma 1 and sigma 3. Now, do we know what is sigma f? Normal stress at failure? Yes, it is given to us, no? 100 kN per meter square. So I substitute this, I get sigma 1 is equal to 100 upon 1 minus sine of 26.6 degrees. That you will get it as 181 kN per meter square. Sigma 3 will be same 100 divided by 1 plus sine of 26.6, that is 69 kN per meter square. Now the angle made by the failure plane with the major principal plane, alpha, right? How is it? What is the equation? 45 plus beta m by 2. That is how much? 45 plus 13.3, 26.6 divided by 2 will become 13.3, that is 58.3 degrees. You got the value. Now you got the value of alpha is equal to 58.3. I have purposely come to this particular, I want you to concentrate on this GOH again now. Alpha you've got it as 58.3. What type of test is being conducted? It's a direct shear test. In a direct shear test, what is the direction of failure plane? It's horizontal, so that GH is supposed to be horizontal. If GH is horizontal and GH makes alpha, that is 58.3 with sigma 1, then does that mean sigma 1 makes 58.3 with horizontal? This is simple geometry. GH is making 58.3 with alpha 1 and GH is horizontal, sorry, sigma 1. So that means sigma 1 is also making 58.3 with horizontal. So I hope this part is clear. We got the value of maximum obliquity as 58, maximum angle of shear failure, that is equal to 58.3, and we know that GH is horizontal and GH is a failure plane. This alpha makes with sigma 1. So that is by logic, by geometry, if this is horizontal and this plane GO is making 58.3 with the horizontal, that means GO is making 58.3 with the horizontal, correct? So I will write here, since failure plane, see that figure is not required, I've just drawn it to explain. Failure plane makes 58.3 with major principal plane, that is sigma 1, and you know that the failure plane is horizontal. That's why sigma 1 will make 58.3 with horizontal. Now this is sigma 1. Sigma 3 is here, correct? Sigma 3 is here. Can you tell me what will be the angle sigma 3 will make with horizontal? This is 58.3. Sigma 3 makes what angle with sigma 1? 90 degrees with sigma 1. Therefore, sigma 3 will make, what will be the angle with horizontal? 180 minus 58.3 minus 90 degrees. That is equal to how much? 31.7 with horizontal. Now let's come to the third part, that is a traction test. Now what you are told to do is you have to find out the deviated stress. What is told to you is sigma 3, that is cell pressure is going to be 60 kN per meter square. Okay, sigma D is what is asked. Okay, so that is asked. This is a question mark. Maximum obliquity of phi is given to you is 26.6 degrees. Okay. Now, to get sigma D, what is the equation between sigma D? Sigma 1 is equal to sigma D plus sigma 3. Correct? So, in that case, I will need to find sigma 1. How do I get sigma 1? I know beta, I know sigma 3. Can I do you have equation between sigma 1 and sigma 3 in terms of beta m? We do have, okay. Sigma 1 upon sigma 3 is given as 1 plus sine of beta m upon 1 minus sine of beta m. Now beta m is same as phi, you substitute it here and you substitute all these values, you have the value sigma 3, you will get sigma 1 is equal to how much? Solve this up, just don't look at this like some fun video. Solve this, okay? You should get these answers. You should get used to feeding in the values of angles. Many a times angles are fed in radian. Sometimes the calculators are in radian modes. You fill the angles in radian modes and you get all the wrong answers. So you should get a hand on your calcs. Okay, just slightly scroll up. Okay. Now sigma 1 you have determined. Next thing is determine the value of sigma D. From this equation I am directly writing this as sigma 1 minus sigma 3, that is 157.4 minus 60 divided by 10. So we have solved an example on cohesion-based soils. We will take another example on cohesive soils so that all the equations which you require in the shear strength chapter, you have it in one particular example, and then I think we are done with the shear stress chapter.